I will give a brief introduction, I guess, about my research, where it started and how it started, and what am I doing now, where am I heading now, and, well, I guess just to get myself, or get you more involved into my research. So the first thing which I would like to start with, that's where I'm working on, so this Poznan Science Park. So you see, I have a photo of actually Potsdam Science Park, Golm. But a part of the research there, a nice invitation to the beautiful Potsdam, which is near to Berlin, because no one knows what is Potsdam, and even less people know what is Golm. So, kind invitation. Potsdam is famous for its castles. I put only 3. There's way more, so it's like for a week for you to come, and especially in the warm time. So. Enjoy the beauty and enjoy the nice science of the Max Planck Society. So to my research. So I'm working in a group which is called Sustainable Solvents for the Green Processes. And where I'm heading to is to try to use some solvents. So the approach is to make the sustainable resources also available by the more sustainable and more safe ways to produce the materials. So it's not only the matter of using the sustainable resources, but also how to approach them in a safer way. So I put here the slides of solvents, so alternative solvents. Probably everyone knows about ionic liquids as an alternative media. So who doesn't know then about alternative to this alternative, which is a deep eutectic solvents. They also do have share a lot of advantages with ionic liquids, but though are a little bit easier to prepare and still remain the advantage of being designed solvents. And I guess what I can also point at, it's a little bit easier from the perspective of safety. So you do know what you put there. So how to use them and what are they very shortly. So this is a very short introduction here in the physics and chemistry of eutectic. So you know that two compounds usually have depletion of the melting point, and this is a physical phenomenon between all the not mixed compounds. But with more interest to these systems in chemistry and more research, scientists pull their attention that actually eutectics are quite abundant. You can find them in nature, you can find them around yourself, so like in the maple syrup and honey, so it's things which you observe and every day. And I was curious how you can actually pull them a little bit more into the chemistry as it is. So to start with, eutectic solvents, despite their all advantages, have one well, not the disadvantage, but not the best thing is they are very viscous. So their viscosity is quite high, and how to decrease it, it's always an issue. So I try to approach it in a very interesting way. I try to substitute one of the components on a slightly smaller molecule, which is ammonium formate. So instead of usually used Holland chlorate. So what I've obtained and what I observed, so they do form eutectics, so which is great. But sometimes components remained as they were, sometimes they not. So, and I started to dig a little bit more into it. So you can see that my example here is a glucose. So what's happening in this eutectic? And generally, it's observed not only for the glucose, so this is a very short introduction here slide. So it's not only glucose which is doing these things in this type of chemical eutectics which I'm working with, but also citric acid, also phenols, and they form a variety of different chemical products. But with keeping in mind the cellulose and biopolymers, I will tell just a few words about this part where the saccharides are reacting with the ammonium formate. So it's a little bit of chemistry here around. This is a very familiar to everyone chemistry. So it's a coffee, it's everything which we're roasting. So it's a Maillard reaction, and it results in this substituted pyrazine. So in the case of fructose, it's usually 4 different isomers, which are obtained also by cooking. They're giving smell, they're giving antibacterial properties and amazing molecules. This how they are usually synthesized in myoeutectics. Shortly into the reaction. So the main idea here to forward you further into the research to biopolymers. So you see there's an Amadori rearrangement, so reductive amination on the glucose unit and amination of this part. So further, these products can be dimerized and resulting in this desoxyfructosazenes. So, but now let's switch into the polymers and into the more into the cellulose research. So there's just to be on the same page with everyone how the cellulose nanocrystals are extracted. You know that this reaction is basically, their extraction is basically based on the different kinetics of the reaction between amorphous regions and crystalline regions, and, well, partial functionalization of the crystals. So, but this is done with acidic hydrolysis, can be done also in the same Amadori reaction. And this is exactly what I did with the cellulose. So I formed different eutectics with multiple natural organic acids like lactic acid, levulinic acid, glycolic acid, adding as a second component ammonium formate. So depending on whether the acid is liquid or solid at the room temperature, I obtain room temperature eutectic and treat cellulose starting materials exactly in this one. So there's a scheme. It's a very nice reactor, which is like a hot press cooker with mixing. So this is where we treat our reaction, and approximately how we imagine that this exactly the same reaction is happening. Reductive amination is happening on the reducing ends of the cellulose chains. So, what do we obtain as a result? Because there's a video which no one knows how to start. As you see from the TEM, our result, and basically also from the video of this, like, I don't know how to start it. It's a typical, looks like a typical CNC crystals. They form gels. They form iridescent films. Seems to be very similar to sulfuric acid. We can see that the crystallinity index is increasing by extracting them. And basically the only difference, which is on the surface, we do have a positive charge of the nanocrystals. And from that on, well, how can we find out what are the properties and what are the applications for them? So the first one, and the very straightforward, which we did, was based on the idea that our particles are not that highly charged. So when CNC crystals are not that highly charged, the best application for them, which is sitting on the top of the head, is probably we can use them as a Pickering emulsion stabilizers. And that's exactly what we did. And they occur to be a very nice Pickering emulsion stabilizers without any kind of further changes, chemical changes. So emulsions, yeah, looks like a beautiful emulsion with nice particles. And the next question was, of course, like, what would you use the emulsions for once they are done? We somehow came up with the idea that additive manufacturing is rising up, and we should try them in the 3D printing. And this is what we did. So for the 3D printing, as is clear, rheology is among the important factors required to have the ink performing with the necessary properties. So what we have is viscoelastic solids that are necessary to have the ink to be printed out. So among them, shear thinning, storage modulus is larger than loss modulus, and appropriate yield stresses. So we check on CNC water emulsions. We have shear thinning behavior. We check storage and loss modulus. They also fit. We don't feed the appropriate yield stress when this is just the emulsion stabilized like that. So what should we do for that? We decided to modify our emulsions to make them more gel, so add something to the continuous phase. Our choice was basically alpha cyclodextrines. Let me see. At the end, we have this nice creamy structure, this creamy ink, which we can print. So why alpha cyclodextrines? Which is an interesting question. So alpha cyclodextrines have this very interesting behavior. Then they can form this moving gels with the PEG. But we don't want to use PEG. So we have to somehow figure it out with this modifying our continuous phase, but still avoiding the polymers. So it occurs that for alpha cyclodextrines, they can form the similar structure also with alkanes. And alkanes, long chains, you can find also in oils. So what you observed, and for such an emulsions, long chains are sticking into the water and can be modified with this alpha cyclodextrines sticking on them, like this. So theoretically, alpha cyclodextrines can also stabilize the oil in water emulsions. CNC as well. They both have appropriate properties, but co-stabilized emulsions are yielding this optimal stress, which allows us to form the inks with the appropriate properties for the 3D printing. So with the help of Rubina, who's an experienced in 3D printing, we tried all of our formulations, because, well, you do know that only having the data on the graphs does not really always mean that they are performing very good for the 3D printing. So we tried them, exclude one, and choose two, which were the best. And here I pay your attention. So also we tried to additionally modify continuous phase with alginate. Keeping in mind that alginate is very known for the 3D printing in biomedicine. So we get an excellent 3D printing properties for the emulsions. Basically, you see here that even quite complex shapes are approachable with this inks as much as quite high printed figures. Objects are with 55 layers with the self-support are also possible with this inks. We also try to freeze dry them and just room temperature dry them and see how they remain their shape afterwards. But again, we have new CNC, and we have to somehow check where they are useful, how they are useful, what's the best thing which we can gain out of them. So another quite famous way to use CNC is to form is that they are able to form quite densely packed films. So in the collaboration with Fraunhofer, which is right across the road from us, we decided to try to make some membranes and see how we can do the gas separation. First thing which we know, again, just CNC without any modification, without any changes or additives, is a barrier, which is actually an excellent barrier. As you can see, this like the permeability is super low and compared to polyethylene. Progressive for packaging and so on. But how to make them into the membrane? So you probably know that membranes are quite not straightforward. Preparation of membranes is a process of basically drying some dissolved polymers. We have a little bit different system. So we have already nanoparticles in suspension, and our idea was if we have the tied film what's of just cellulose, we can kind of dilute it with ionic liquids, keeping in mind that they will be highly sensitive to CO2, and this way we can have CNC as a support for the ionic liquid and a membrane formed that way that we can separate CO2. So we did. And as I said, membranes are not that straightforward, even if they are made out of the dissolved polymers, and even less if they are made out of the particles. So we found out that mixing the components is an issue, making them homogeneously interacting with ionic liquids is an issue. So ionic liquids is highly charged, of course. When it's put together with the charged CNC, we change the ionic strength of solution. So we have agglomeration, we have increase due to the increase of ionic strength and low reproducibility of the results. So you see, it shows here, so the permeability of some membranes just jumped, of some not. And the difference between the gases separation is not that vivid. So how to avoid this? Dragons, and troubles with preparing the membranes of CNC with ionic liquids. And here comes, again, plasticizing and again, this interaction of the biopolymers as they are in nature. So we turned our heads into the natural components of xylenes, hemicellulose in wood. So it stabilizes cellulose in the wood. And in the same way, we decided, okay, it's a famous plasticizer for the cellulose particles. And that allowed us to actually obtain the very nice reproducible cellulose membranes with ionic liquids, no cracks, and almost no agglomeration. So we prepared different films, used for them cellulose of different sources with the shorter fibers and with the longer fibers. See the morphology of them. They are usually this kind of a layered morphology of all of them. But the interesting thing, which we found out by measuring these membranes, um, and we are still a little bit puzzled about it. This is some kind of weird interaction between the ionic liquids and cellulose, which gives absolutely counterintuitive gas separation. So CO2 basically goes slower than nitrogen, which is not expected, and probably somehow related to the interaction with ionic liquids, which is to be researched. So another field, as I was mentioning, and which is absolutely very interesting for the industry, for us as a sustainable people who wants to have less pollution, less polymers thrown away. It's a barrier of nanocellulose. So we did step in there also a little bit and try to cover the cellulose paper with the nanocellulose. So our idea there behind was to have better contact with the cellulose, which is usually negatively charged, of our nanocellulose particles. So you can see with less loading of the CNC, it's kind of like wraps around all the fibers. I would suggest the positive charge of the nanoparticles plays its role there. We found the optimal load of CNC to cover the surface completely. And and on top of made a cross section of it. So we do see a very, very nice layer of the CNC, very dense, nice layer of the CNC. We made absolutely straightforward test if we can remain the oil on one side of the samples, which is, yes, so it stays there forever. I guess it still stays somewhere there in our drawers in the lab. That's about it. So that was just a short introduction into what we're already did, what kind of achievements, results do we have. So shortly to conclude, there are eutectic mixtures, and to go a little bit more into the research which I'm doing right now. So we do use them not only to prepare the nanocellulose, but also you can turn around and see how nanocellulose is interacting with them in the similar way as we see them eutectics in nature. But you do can prepare then extract the nanocellulose using the eutectics, which makes this method quite sustainable and less toxic. Small nanoparticles of nanocellulose can form the dense layers on the paper of this positively charged nanocellulose, as much as with preparing the membranes with the ionic liquids forms the good let's say the interesting membranes for the gas separation with very unexpected properties, and low charge of these particles allows us to do this in 3D printing. With the outlook, so a little outlook into the things which we're planning to do. So basically, we're quite inspired by this biomaterials, and we decided that we will not stop only on the cellulose. So we tried to extract hemicellulose, which I'm now very happy to be on this conference and to see also how other people are looking on this biopolymer. So I'm personally very keen on this photos of the hemicellulose extracted with a different time of extraction, and as much as also we're kind of inspired by the nanolignin and how this can interact, especially since the nanocellulose is positively charged, whether we have can obtain some better interaction for some also construction materials and so on. So at this point, thank you. I would like to thank to Marcus for his support, for his ideas, for inspirational talks. So also to my group, you can see there's also happens winter in Germany, so there was snow one day. And thank you everyone for your attention.